In the last video, I defined and studied principal ideal domains. These are special classes of rings where very nice property holds that every ideal is principal. So in this video, we are going to study a more important class in some sense of rings and a more general class. Certainly it includes PIDs, is this notion of unique factorization domains. So these are nice rings which cover most of the interesting examples that we have studied in this course, and which this property that we want to define is very important. Principal ideal domains are also very nice, but the property is too special. Many nice rings don't have that property. For example, the ring ZX is perfectly good ring, but it is not a principal ideal domain, but it is a unique factorization domain, as we will prove in this course. Okay, so unique factorization domains are an important class of rings. So as the name suggests, we are going to ask for the following property. We want every element to have a factorization into irreducible elements, and that factorization should be unique, essentially unique. I will define what unique means. But the model to keep in mind is the following. Is the model that you are familiar with. Is the ring of integers, and in school you all learned that every integer can be factored into a product of prime numbers. Prime numbers are irreducible elements in the integers, because in the set of in the ring of integers, irreducible and prime are really the same notions. So model to keep in mind, in the ring of integers we can say that every integer can be written essentially uniquely. I will say why I will put this in quotes and say essentially, can be written uniquely as a product of prime integers. So I am going to call them prime integers now, because in an arbitrary ring also we are going to talk about prime elements. So prime integer is actually a prime integer, the way we have learned it in school, right? For example, 30 can be written as 2 times 3 times 5. But it's not quite unique, because I can also write it as minus 3 minus 2 times minus 3 times 5. And now I am going from the notion of prime integers that we've learned in school, which under which notion a prime number is has to be a positive number. But in the more general notion of prime elements in an arbitrary integral domain, Z is an integral domain, so there is no reason to exclude negative numbers. So minus 2 is also a prime element. So, and hence it's an irreducible element. So we can write it like this. So we will not treat this as different. Right? Because the way that we will not treat this as different is, we will consider 2 and minus 2. Appearance of 2 and minus 2 is the same. That means whether 2 comes or minus 2 comes, we are not going to make a difference, because they are associates. That is a crucial statement there. So now this is the model, as I said, to keep in mind. We want to see whether this can be carried over to arbitrary integral domains. Can we now say that any element in that ring can be factored like this, and if possible uniquely? Okay, so the question is, what we have learned in school is that in integers you can do this. Question is, how much of this is possible in an arbitrary integral domain? So if you go to an arbitrary integral domain, how much of this is possible? So first of all, we want to factor. So how do we go about factoring? So let R be an arbitrary integral domain. So we'll put some conditions later and define unique factorization domains. But let's start with an arbitrary integral domain, and let's take an element R, element A. So how do we factor A? How do we factor A? So this is what we do. So how do we factor A into a product of irreducibles? If A is irreducible, we stop. So it's sort of an algorithm. So if A is irreducible, we stop. There is nothing to do. A is its own irreducible factorization. For example, number 5 in the ring of integers is irreducible. So you don't do any more work. You stop. So if A is irreducible, we stop. If A is not irreducible, by definition, A can be written as A1, B1 for some A1, B1 in R, which are not units, right? Which are both not units. Because if A is not irreducible, we know that there is a proper divisor. If A1 is a proper divisor, we can find another proper divisor B1 such that A is A times A1, B1. So we have gone from A to A1, B1. If A is irreducible, we stop. Otherwise, we find two other elements A1, B1. If A1 is irreducible, we stop here. And if B1 is also irreducible, we stop. And that's the irreducible factorization. If both are irreducible, we stop with the factorization given by A1, B1. If either of them is not irreducible, we continue. Right? A1 factors properly as a product of two non-units. B1 factors properly as a product of non-units, and we look at those 4 elements. If they're all irreducible, we stop here. Or so we may stop at any stage. If at any stage we have all irreducible elements, we stop, and thereby we achieve our irreducible factorization. Otherwise, we will continue. Right? And potentially we may have to continue forever. So we say that factorization, so the question is, can we continue? Is it possible to continue forever? So that will not be good, right? If you have to continue forever, that means there is no factorization for A, because you cannot, only if you stop somewhere, we achieve a factorization of A. So we say that factorization terminates in R. We say that factorization terminates in R if the above process stops or terminates somewhere for every A in R. So if it stops for every A, we start with some, if it's irreducible, we stop. If not, we factor it. If the two factors are irreducible, we stop. If not, we continue. We factor those two and then keep continuing. Suppose it stops somewhere for every element in the ring, then we say that factorization terminates in R. So that's a phrase. So it's a property of a ring. So the statement is, hence the conclusion is, if factorization terminates in R, then every element of R has an irreducible factorization. Okay, so this is clear, right? If factorization terminates in R and you are given an arbitrary element of A, arbitrary element A of R, we continue the process described in the previous page. If it's irreducible, we stop. If not, we factor it. If the two factors are irreducible, we stop. If not, we continue factoring them. And eventually it stops because I am assuming that factorization terminates in R. That's a phrase. That phrase says that for every element this process stops. Obviously then every element has an irreducible factorization. We are not yet coming to uniqueness. I am currently only interested in establishing when factorization actually exists. So it exists when factorization terminates. I should right away warn you that in general factorization may not terminate, as the following example shows. In general, factorization may not terminate. So the above process I described may never stop. As an example, let's look at the following ring. Let's look at the ring given by z adjoint square root 2, 4th root of 2, 8th root of 2, 16th root of 2 and so on. Okay, so this is actually a subring of the real numbers where I am adding square root of 2, 4th root of 2, 8th root of 2 and so on. So any element of this ring is a finite sum of some integer times an element, some 2 power nth root of 2 plus another element times 2 power n 1th root n 2th root of 2 and so on. So elements are like this. For example, this is an elements. Okay, so it can also be some 124th 128 rather root of 2, some 3 times this minus 256th root of 2 and so on, right? So this is a ring. Any such combination you take, in fact I can take squares, any powers and it will be an element of this. So these are elements. I claim that in this ring in R 2 has no factorization. Because let's follow the algorithm that I described earlier. So 2 is not irreducible because it is a product of square root 2 and square root 2, right? Neither of them is a unit. But square root 2 is also not a irreducible element because it is 4th root of 2 times 4th root of 2 and then also 4th root of 2, 4th root of 2. So basically what I am saying is that you can continue this, right? This is 4th root of 2 power 4, but I can also do 8th root of 2 power 8, 16th root of 2 power 16, 32th root of 2 power 32. Where do you stop? There is nowhere you can stop. 2 has no finite factorization. You can't say this is a factorization because 32nd root of 2 is not an irreducible element. It actually further becomes 64th root of 2 squared, that is 32 square root 32nd square root of 2 is 64th square root of 2 square. So you can keep doing this. At any stage you don't have a factorization. So you have to keep going. So this is a strange ring. Of course it won't happen in most common rings, and I will tell you, for example, it doesn't happen in Noetherian rings as we will see later. So immediately we conclude that there is no hope of doing factorization in any integral domain. So this is certainly an integral domain, right? R is an integral domain because it's a subring of the real numbers. So certainly factorization is not possible, leave alone unique factorization. Factorization itself is not possible in all integral domains. It's too bad, right? We were hoping that maybe what happens for the integers can be carried forward for every integral domain, but that's not the case, as this example shows. So we have to ask for, so we must have the property that factoring or factorization terminates in R. Right, so this we have to ask. It may not be true for every integral domain as this example shows. So we have to ask for as a special property of R. So this must happen. So this is a special condition. But now let's come to uniqueness. Let's come to uniqueness. Okay, so now remember, uniqueness on the nose is not true even for integers because the factorization 2, 3, 5 and factorization -2, -3, 5 should be considered really same, though the exact elements that appear there are not same. So what is the notion of uniqueness that I want to define? So we say that A has unique factorization if a small a, so I want a small element, I say element small a has unique factorization if the following happens. Given any two, so first of all, if A has factorization into irreducibles, that must be happening into irreducible factors. Otherwise, if there is no factorization, there is no point talking about uniqueness of factorization. So first of all, it has a factorization, and if we have two different factorizations, P1 through Pm is equal to Q1 through Qn, are two different factorizations. Whenever I say factorization, I mean factorization into irreducible factors. That means P1 through Pm, Q1 through Qn are both irreducible, are all irreducible elements. Then we must have m equal to n, and after reordering, if needed, Pi is an associate of Qi for all I from 1 to m. So 1 and m and n are same to begin with, and after reordering, because we have to reorder possibly. See, 2, 3, 5 is same as minus 3, 5, minus 2, right? So unless you reorder, you can't say 2 and minus 3 are associates. So we reorder one of them, then there are 3 factors here, that's m, and there are also 3 factors here. So m and n are equal, and after having rearranged, 2 minus 2 are associates. Of course, in the ring of integers they are associates. 3 minus 3 are associates. And of course 5 and 5 are associates because they are actually equal elements. So this is exactly what we mean by unique factorization. Not quite that elements are equal, but elements are associates. Another example, I will write Zi, which I told you as a fact last time that it's a PID. In fact, it will turn out to be UFD also after we prove that every PID is a UFD. But in this ring, we have 2 plus I times 2 minus I is 5, because 4 plus 1. But this is also equal to 1 plus 2I, or rather I will write maybe 1 minus 2I and 1 plus 2I. Okay, so these two are associates because you multiply this by I or minus I, you get this, and these two are associates. You multiply this by I, you get I squared minus I squared is 1, 2I. So this is also unique, these factorizations are unique, or rather are for all practical purposes they are considered same. So these factorizations are same. So now I am ready to define the main definition of this video. An integral domain R is a UFD. I will use the short abbreviation UFD for unique factorization domain. So it has two properties. Of course, it has two properties. There are two words, right? It's three words really. Unique factorization domain. So it has to be an integral domain. That's for D. Factorization must exist. So factoring terminates in R. This must happen so that every element has a factorization, and two irreducible factorizations of any element is unique for all A in R. So unique in the sense of this. So I say that they are unique if the number of irreducibles must be equal, and after reordering if needed, the first one is an associate of the first one, second one is an associate of the second one, and so on. So this second property is the uniqueness, first property is the factoring, and the hypothesis that it's a domain takes care of D. So a unique factorization domain is one which is an integral domain where factoring terminates, and because of the first property, every element has a unique irreducible factorization, but irreducible factorization must be unique. Okay, so now in this rest of this video and in the future videos, we are going to study properties of unique factorization domain. So let me prove a proposition to get control of the first property. See, factoring terminating seems a difficult condition to check. So I want to do a proposition to simplify that process. Let R be an integral domain. Then the following are equivalent. So this is standard notation for TFAE. It means the following are equivalent. TFAE, the following are equivalent. So what are the two statements that I want to make here? Factoring terminates in R. Factoring terminates in R, which is what we are interested in finding out. And the second condition is that any ascending chain of ideals, not just any ideals, in fact I want any ascending chain of principal ideals, stabilizes. So this notation should remind you of the video when we were talking about Noetherian rings. Recall that a Noetherian ring is a ring where every ascending chain of ideals stabilizes. We did not put the word principal there. So this is a weaker condition. Any ascending chain of principal ideal stabilizes. So in particular, a Noetherian ring will have the second property, hence it will have the first property. So in any Noetherian ring, factorization terminates. So let's prove this. So I will prove this is very simple. So let's prove 1 implies 2. Suppose factoring terminates in R. And let us take an ascending chain of primes, principal ideals rather. Let's consider A1 contained in A2, contained in A3 and so on. So I'm trying to show that, assuming 1, I want to show that any ascending chain of principal ideals stabilizes. Suppose not. Suppose you have an ascending chain of principal ideals which does not stabilize. So then we will show that then A1 has no factorization. Okay, that is because which violates then that factoring terminates, because if this continues like this, what we have is A1 can be written as A2 times B2, right? The fact that A1 is contained in this means A1 is in the ideal generated by A2, that means A2 times B2 for some B2. So A1 can be written as A2 B2, but A2 is in the ideal generated by A3, which means we have A3, B3, B2. So I am retaining B2 as it is, but A2 can be written as A3 times B3. And remember, if this chain does not stabilize, this statement here implies AI is not a unit for any I, right? If AI is unit for some I, that means the ideal generated by AI would be the unit ideal, but unit ideal will be equal to R. So beyond that, everything is unit ideal. That means the chain has stabilized. Stabilizing means after some finite stage, they are all equal. So if A100 is a unit, the ideal generated by A100 is R. That means A101 is also R. A102 is also R. So beyond 100th stage, everything is R, but then the chain has stabilized, which we are assuming has not happened. It does not stabilize. So it's not a unit. That means these are all proper factorizations. So you can continue now. A4, B4, B3, B2. So I've carried over B3, B2, and written A3 as a product of A4, B4, and then it keeps going. So it is a simple exercise now to show that this tells us that, see, none AIs and BIs may not be reducible, but if A1 has an irreducible factorization, you cannot keep forever factoring like this. A1 has no proper factorization. Sorry, A1 has no irreducible factorization. If there is a chain of principal ideals which does not stabilize, the first one or any one of those cannot have a factorization. This contradicts 1. So it must be the case that 1 implies 2. If factoring terminates is given, an ascending chain of principal ideals must stabilize. So let's prove 2 implies 1. So this little thing I will leave as an exercise for you to convince yourself that if A1 has an irreducible factorization, you cannot possibly keep forever factoring A1. Now let's prove 2 implies 1. So now I am assuming 2. I am assuming that there is a, given any chain of principal ideals, it stabilizes. So let small a be any arbitrary element. I want to show that the algorithm that I defined at the beginning of this video terminates. How, recall what was the algorithm? If A is irreducible, A has a factorization. So suppose, so actually I am going to assume that 1 is false and get a contradiction. Suppose that A has no factorization. I am trying to show 1, right? I am assuming 2 and I am trying to show 1, which is that factoring terminates in R, which is another way of saying that every element of R has a factorization. Suppose that there is an element of R called A which has no factorization. That means we could have factored A as A1, B1, and we would then factor A1 as A2, B2, A2 as A3, B3, A3 as A4, B4, and so on. Right? This must continue forever. This algorithm continues forever. That is the meaning of A having no factorization. But that means the ideal generated by A is in the ideal generated by A1, right? Because A is A1, B1. Ideal generated by A1 is in the ideal generated by A2 because A1 is A2, B2. Similarly, the ideal generated by A2 is in the ideal generated by A3. And this continues forever. This does not stabilize. That is the meaning of our algorithm does not stopping anywhere. That means this does not stabilize because at each stage we have a proper factorization. So for example, the ideal generated by A4 is strictly bigger than ideal generated by A3. If it was not, A3 and A4 would be associates. So B4 would be a unit and you would have stopped. So somewhere, actually I should be more careful, somewhere in this tree we have an infinite chain. Maybe it stops here, but B3 we factor it does not stop there. So wherever it doesn't stop, if you trace through that path, we get an infinite chain of principal ideals which does not stabilize. So this is not quite correct because it may be that this stops but somewhere else it doesn't stop. But doesn't matter. I can assume without loss of generality that this doesn't stop. So this does not stabilize. So 2 implies 1. So the advantage of this proposition is that we are able to conclude if R is a Noetherian integral domain, then in a Noetherian integral domain, then factoring terminates in R, right? So in other words, every element of R has an irreducible okay. So Noetherianness is too strong a property because in Noetherian rings, every ascending chain of ideals stabilizes. Whereas for factoring to terminate, we only need that every ascending chain of principal ideals to stabilize. But still, if you have a Noetherian ring, we can be sure that factorization terminates, and hence every element has a irreducible factorization. It is not going to imply that irreducible factorization is unique, but at least you are guaranteed that factorization terminates, so that every element has a unique has a factorization. So now I will end this video by giving an example. Even if factorization exists, it may not be unique. Okay, it may not be unique because as the example, our favorite example, this is something that we have considered before. R, I will take Z adjoined square root minus 5. This is providing us all the examples that we are interested in, right? It gave us an example of an irreducible element which is not prime. It gave us an example of going to give us an example of something which where unique factorization is not unique. So, and this is something we have seen before. Okay, so what I will leave for you is to show that these are distinct. They are actually not same as I defined earlier. When do we call two factorizations same? The number of irreducible factors that appear are same, is equal, and up to reordering they are associates of each other. So what you have to do is 2 and 3 are irreducible, 1 plus square root minus 5 and 1 minus square root minus 5 are irreducible. So these are both irreducible factorizations, but 2 is not an associate of either of them. This is something that came up earlier, and this can be proved by proving this fact. Only units in R are 1 and minus 1. So there are no other units. So if 2 and either of these elements is are associates, if for example 2 and 1 plus root minus 5 is associates, 1 plus root minus 5 will be 2 times a unit. But this says that only units are 1 and minus 1. But 2 times 1 is 1, 2 times minus 1 is minus 2. Neither of them is equal to 1 plus root minus 5. So this is the exercise that I want you to do. And I want to also prove that 2 is irreducible, we have proved. Using the same argument, prove that 3 is irreducible. And similar argument tells you that 1 plus root minus 5 and 1 minus root minus 5 are irreducible. So these are distinct irreducible factorizations. So this is not unique, and hence this ring is not a UFD. Right? Though actually it turns out that this is a Noetherian ring. So it is in this ring factorization terminates. So every element has a factorization into irreducible elements. However, as this example shows, this is not a UFD. So this is an important example which provides various counterexamples to things. So what I want to do next in this video, we have learned what UFDs are. These are rings where factorization exists and is unique. And we have proved that in a Noetherian ring factorization exists, but it may not be unique, but factorization exists. And in even more bad rings like Z adjoined power roots of 2 power nth roots of 2, even factorization does not exist. And in a nicer ring like Z adjoined square root of minus 5, factorization exists, but it's not unique. In the remaining next few videos, we are going to look at more examples of UFDs. In particular, we will prove that a PID is a UFD. So that gives us a collection of nice examples of UFDs. And we will prove that there are some rings which are not PIDs but which are UFDs. So that's for the next video. Thank you.